Welcome to my ELM test prep series. I'm James, and what we're going to look at in this particular episode, part 20, is distance problems. And the fundamental equation for distance is distance equals rate times time. Rate is can be referred to as speed or velocity. Time can be in hours, minutes, seconds, doesn't matter. Distance can be in any number of things. It could be in meters, miles, it could be yards, feet, inches, it doesn't matter. Those are just categories or particular units of our problem. One of the basic, and I'm just going to write this in terms of distance equals rate times time, or what I fondly call my dirt formula. One of the basic problems, dirt problems, would be, okay, I'm traveling at some rate in my car, say 60 miles per hour, and I'm traveling for a time of 2 hours, and I want to know the distance I traveled. Well, distance equals rate times the time. So this would be 2 times 60, which would be 120. And if I multiply my units, miles per hour times hours, the hours cancel out, and we can see that my distance would be 120 miles. That's a fairly straightforward dirt kind of problem. They might change around a little bit, ask you, they would give you the distance traveled, 120 miles, they would tell you the rate, 60 miles per hour, and then they want to know the time. So then I would just divide 120 by 60, and then I would get my time. So I would have miles divided by miles per hour, and so if I invert and multiply, I get hours over miles, and the miles cancel, and I get time in terms of hours. So, distance traveled, rate times time. The more subtle kind of dirt problem is one in which it doesn't look like I'm traveling the distance. Let's say I'm doing a job, whether it's painting a room, putting a roof on a house, building some kind of widget. I think of the job in terms of I start the job out here and then I travel to the end of my job. Well, this is a distance traveled. If I can do the job in 3 hours, then I did 1/3 of the job in the first hour and 1/3 in the second hour, assuming an average rate of work, and 1/3 in the last hour. So from this standpoint, in 1 hour, I did 1/3 of the job. So my rate, you might say my rate is 1/3 of the job per hour. Each of these hours I'm doing 1/3 of the job. So it is a quantity that I'm doing. So after 2 hours I would have 2/3 of the job done. Well, typically they give you a job where they say maybe Bill takes 3 hours to do the job and Jan takes 2 hours to do the job. And so we ask ourselves, what's the rate that Bill works at? Well, he works at 1/3 of the job per hour. Just invert the 3. Jan works at 1/2 of the job per hour. So if they work together, I'm going to essentially add their quantities. Bill did a certain quantity in the first hour, and so did Jan. So if I add them, I'm going to have 1/3 of the job plus 1/2 of the job, and I want to know what time it takes them to get the job done. Well, the distance is job. If I do rate times time equals distance, the time they worked the same time. They worked at the same time. So essentially the distance is the same, so it becomes a relationship between the two of them. And I ask them, if I'm doing this job, well, 1/3 was done and 1/2 was done. So in that first hour, if we do a common denominator here, we end up with 5/6 of the job was done in the first hour. Well, we can see that my job is quickly going to get done here with the two of them working at it. So in the first hour, they did 5/6 of the job. 1/3 plus 1/2. Well, it's not going to take much longer to finish the job since I only need another 6. So the question is, well, how long is it actually going to take? So I say that I'm doing 5. My rate is 5/6 of the job per hour. And that's my rate times some time. I don't know what that is, but I know my job is one job. So if I just divide this, both sides by this 5/6, or in other words, multiply by the inverse, 6/5, I'm going to multiply 1 times 6/5, and this is hours per job. And this is one job, and so the units will cancel, and I'll end up with 6/5 to do the job. My time is going to be 6/5 hours, or 1 1/5 hours. And then of course I could figure out what those minutes might be if I wanted to know the time in minutes. But in terms of estimating this job, let's say we have this problem on our test and I want a quick estimate. Well, if they both worked the same time, let's say they both worked at 3 hours, well, they're doing 1/3 and 1/3, so that's 2/3 that they're doing at any one time. So it should take them half the time that one person could work, or 1 1/2 hours. Well, that's not bad. So 1.5 hours if they're both working at 3. But let's assume that they were both working at 2. Since Jan can work at 2, maybe she inspires Bill to work a little faster. So they're both working at a rate of 2, 1/2 the job per hour. So I'm going to combine that and say that, well, if they work together, it should only take them 1 hour. So the time that it's going to take them working together is somewhere between 1 and 1.5 hours. And we said it was 1 1/5 hours, which is 1.2 hours. And sure enough, that falls between 1 and 1.5 hours. So if I needed a quick estimate on this answer, I might just do that estimate, set up and say, well, half of 3 is 1.5, half of 2 is 1, and my actual time falls somewhere in between. And depending on the answers they give you, you may be able to just jump right on the answer. Alright, so that is a work-related problem where something happens and two people can do it individually at a certain time, but they work together. Okay, so one of the other typical problems is what we call upstream downstream, where I may be rowing up a stream and it takes a certain amount of time up, and then I row back down to the same place, and so it takes a certain amount of time to go down. And they'll say, well, maybe this is it took me 3 hours to row up the thing and 2 hours to row down. Well, the question is, what happened? Well, the obvious guess is I have some kind of current that is flowing against me when I'm going upstream, some current. And so my rate here, if I were in free water, my rate, I just take 1/3 of this. My rate would be 1/3 of the distance per hour. But with a current, I have some basic rowing speed in still water. Well, the rate going up the stream is actually rate minus the current. That would be the rate that I'm rowing at. And when I row down the stream, it's going to be that still water rate plus the current. So I might look at this problem in terms of that kind of situation. Well, obviously, rate times time equals distance. Well, the distance was the same. So I could say the rate up times time up equals the rate down times the time down. And I could set up an equation like that. The problem is my rate isn't just a single number. So if I were to substitute this, and I'm going to go back to the rate up the stream is really rate minus current times the time up equals the rate plus the current, times the time down. Well, I've got three variables: rate in my rowing speed in still water, the current speed of the river, and the time. Well, I need two of these, and lots of times they'll give me these two, but they might give you the current speed, and of course they give you the time up and time down. So with that, you should be able to find out, juggling the equation around, find out what the actual speed is that I can row in still water. And that might be the question they ask you. The key here is to put your rate in terms of some still minus the current, some still speed plus the current, and then the time differences between them. Plug in your values and solve for your unknown value. All right. Well, thank you for paying attention. And this was essentially a distance rate time problem, or several of them. Hope that was helpful. Have a good day.